Before we begin, take a close look at this setup. At first glance, it might look like nothing more than a collection of pipes, valves, and fittings. But in reality, this is a complete pneumatic control system similar to those used in factories and industrial automation. By the end of this video, you'll understand exactly how compressed air flows through this circuit, how each valve performs its function, and how a double-acting cylinder automatically extends and retracts. If you've ever struggled to understand pneumatic diagrams or wondered how all these components work together, this lesson is for you. Let's get started. The first component in any pneumatic system is the air supply. In this setup, compressed air is produced by the air compressor. The compressor is fitted with a pressure gauge that allows us to monitor the air pressure before it enters the circuit. However, the air coming directly from the compressor is not yet suitable for operating pneumatic equipment. It may contain moisture, dust, oil particles, or pressure fluctuations that can reduce the performance of the system. That is why the compressed air must first pass through an FRL unit. FRL stands for filter, regulator, and lubricator. Each of these performs an important job. The filter removes dust, dirt, and moisture from the compressed air. The regulator allows us to adjust the air pressure to the correct operating value. And the lubricator, when required, adds a fine mist of oil into the airflow to reduce wear inside pneumatic components. Without proper air preparation, valves may stick, cylinders may wear out faster, and the entire system may become unreliable. This is why air preparation is one of the most important parts of any pneumatic installation. Once the air has been filtered and regulated, it leaves the FRL unit and enters the air distribution block. Think of the distribution block as a junction. Instead of connecting every valve directly to the compressor, the distribution block provides a central point where compressed air can be supplied to multiple components at the same time. This makes the circuit much neater, easier to maintain, and much easier to troubleshoot. From this distribution block, compressed air is supplied to every valve that requires an air source. Now let's move to the heart of this pneumatic circuit. This is the 5/2 directional control valve. The name may sound complicated, but it is actually very simple. The number 5 represents the 5 ports on the valve. The number 2 represents the 2 operating positions. The pressure supply enters through port P. The working ports are port A and port B. These ports connect directly to the 2 sides of the double-acting cylinder. The remaining ports are the exhaust ports, where air leaves the valve after completing its work. This valve is responsible for deciding which side of the cylinder receives compressed air. When the valve changes position, the airflow changes direction. As a result, the cylinder either extends or retracts. Without this valve, the cylinder would never change direction. It is the brain of the pneumatic circuit. Next, let's examine the double-acting pneumatic cylinder. Unlike a single-acting cylinder which uses air in only one direction, a double-acting cylinder uses compressed air for both extension and retraction. One air port pushes the piston outward. The second air port pushes it back inward. This provides greater control, higher force, and much better positioning. That is why double-acting cylinders are widely used in industrial automation, packaging machines, assembly lines, material handling systems, and robotic equipment. In our setup, port A of the directional control valve connects to one end of the cylinder. Port B connects to the opposite end. As the valve switches, the airflow alternates between these 2 ports, causing the cylinder rod to move back and forth. Now let's look at the roller lever valves. These small valves are extremely important because they provide position feedback. Each roller valve is mechanically operated. When the moving cylinder reaches a certain position, it presses the roller. That simple mechanical movement changes the internal airflow of the valve. This creates a pneumatic signal. In this setup, the first roller valve is connected to the Y pilot port of the directional control valve. Its purpose is to control the extension of the cylinder. The second roller valve is connected to the Z pilot port. It controls the return movement of the cylinder. Together, these two roller valves create an automatic reciprocating sequence. Instead of someone manually changing the valve every time, the cylinder itself triggers the next movement. This is one of the fundamental principles behind pneumatic automation. Now let's connect everything together. The compressor supplies compressed air. The air enters the FRL unit, where it is filtered and regulated. From there, the clean compressed air enters the air distribution block. The distribution block supplies air to every valve through the pressure ports marked with the letter P. The pressure port of the 5-to-2 directional control valve is connected directly to this air supply. The working ports A and B are connected to the two ports of the double acting cylinder. The pilot port Y is connected to the first roller valve. The pilot port Z is connected to the second roller valve. Once all the tubing is connected correctly, the pneumatic circuit is complete. Now let's watch the sequence. The compressor is switched on. Compressed air flows into the FRL unit. After filtration and pressure regulation, the air reaches the distribution block. When the cylinder reaches the first roller valve, the roller is pressed. That pneumatic signal shifts the directional control valve. The airflow changes direction. Compressed air now enters the opposite side of the cylinder. The cylinder retracts. As it reaches the second roller valve, another signal is generated. The directional control valve shifts again. The entire sequence repeats automatically. This continuous extension and retraction is known as reciprocating motion. Now let's discuss some common troubleshooting tips. If your cylinder refuses to move, first check that the compressor is supplying enough pressure. Next, inspect the FRL unit to ensure air is reaching the circuit. Then verify that every tube is connected to the correct port. Check that the directional control valve is switching correctly. Finally, make sure both roller valves are being pressed properly by the moving cylinder. Most beginner problems are caused by incorrect tubing, insufficient pressure, blocked air passages, or incorrect valve connections. Fortunately, these issues are usually easy to identify once you understand how the circuit operates. One of the best ways to reinforce what you've learned today is by recreating this exact circuit in simulation software, such as Festo FluidSIM. Simulation allows you to see the airflow, valve switching, and cylinder movement before working with real equipment. Once you understand the simulation, building the actual circuit becomes much easier. Let's quickly recap. Today we've learned how compressed air travels from the compressor through the FRL unit into the air distribution block through the 5-to-2 directional control valve and finally into the double-acting cylinder. We've also seen how roller lever valves provide automatic feedback that changes the direction of the cylinder, creating a continuous reciprocating motion. Understanding these basic principles will make it much easier to read pneumatic diagrams, build circuits, and troubleshoot real industrial systems. If you found this lesson helpful, please give the video a thumbs up and subscribe to Bob Teaches Tech for more practical lessons on pneumatics, PLC programming, industrial automation, and mechatronics. You can also find a detailed written version of this lesson on bobteachestech.com, where I explain the circuit step by step with diagrams and additional learning resources. In the next video, we'll draw this exact pneumatic circuit from scratch, explain every symbol, and then recreate it in Festo FluidSIM before comparing the simulation to the real hardware. Thank you for watching, and I'll see you in the next lesson.